So welcome back. So we have this one more talk before the lunch break. So this is going to be David Kaiser. David has a fairly unique profile here at MIT, I think that's fair to say. Not only is he a professor of physics, he works on cosmology. He's also a professor of the history of science, and so you may have read some of his books on various interesting topics of what happened in the past in the scientific endeavor. He also recently served a term working with the Social and Ethical Responsibilities of Computing office here at MIT. And so today he's going to tell us about how generative AI and the natural sciences are going to come together, I guess, and do something amazing.
Great, thank you. Thank you, Mike, and thank you to the organizers. Been really head-spinning in a very exciting way for me to be able to hear so many of these talks. And so I want to just start with very briefly, picking up where Mike was just saying, what brings me to the topic and therefore the workshop. And so my work in physics is predominantly in early universe cosmology, and especially the last 5 or 6 years, that's given me the opportunity to do some modest scale computation, nothing nearly so complicated or frankly exciting as what I've been learning about from the rest of you, but includes things like trying to model the highly nonlinear dynamics of, say, the onset of cosmic inflation amid a highly inhomogeneous patch of space-time, or using lattice simulations to understand what might have happened at the end of inflation, the so-called reheating epoch, that at the end of which should produce a hot thermal plasma of relativistic particles. More recently, I got very excited, as many of us have, about primordial black holes, especially if they might be a good candidate for dark matter. And that's led to things, again, very familiar to all of you here, like by now quite standard MCMC analyses for families of models. And can you match, an array of observational constraints from different data sources as you vary model parameters, that kind of stuff. So this is the level I've already maxed out by showing the slide, and to be clear, all these were done not by me, but by my much smarter, younger collaborators. But these are examples of trying to use some of these kind of baby methods in scientific computation to ask these questions, in this case, out in the universe. And as Mike just mentioned, I've also been conducting research now for quite a while in the history of science and technology, in a series of books and edited volumes. I'm trying to make sense of not just sort of intellectual trends in various fields and subfields, which is actually really fun, but also how has the course of scientific research been immersed in a changing set of institutions of infrastructure, what are the roles of politics or economics or public policy shifts and so on. How is that kind of helping to shape the direction with which fields like, say, high-energy particle physics or the emergence of quantum entanglement as a really hot topic and so on. How do we make sense of these, the elements of the evolution of parts of, in this case, modern physics, as being tethered to, being conducted within institutions that have their own kind of histories and politics and constraints. And so it was that combination that brought then me, as Mike has mentioned, I was invited a couple of years ago when our new College of Computing at MIT was launched about 5 years ago. I was asked if I would consider trying to kind of design and then launch this new cross-campus multidisciplinary program in what we call SERC, Social and Ethical Responsibilities of Computing. And I was wearing mostly my social sciences hat for that. And I was paired up with a really amazing colleague and now very close friend, Julie Shaw, who's actually a real expert in machine learning, human-machine interactions, robotics. So Julie was coming more squarely from very advanced, fancy computing things, and I was coming from how do we think about kind of contextual issues, and we worked very, very hard on that. We've since passed the baton on to other colleagues, but both you and I say are still connected with these efforts in CERC. And as you'll see, I'm trying to draw on that experience for some of my remarks today. And then most recently, I was invited to serve as an advisor for a working group from the National Academy of Sciences, which I'll talk about near the end of my presentation this morning, trying to sort of think about or make a framework with which to continue thinking about opportunities and also some possible challenges for things like not just AI, but especially quite modern or recent generative AI in the natural sciences in particular. And for that effort, I paired up with a very dear friend, Mark Hagenoff, who's an historian of computing. We wrote a kind of briefing paper that's now available on the Academy's online magazine, Issues in Science Technology, and so on. So there's lots of things, that's where I'm coming from. That's what brings me to the topic and therefore the workshop today. So I want to briefly talk about some of the things that came front of mind for me, especially when I was in the earliest stages of working on SERC, Social Ethical Responsibility Computing. And then I'll shift to a kind of parable that I find really telling. I'll walk through my friend Bruce Bassett's work that I think is something that I find really, it sticks with me. So I want to share that with the group here. And then just briefly at the end, I'll talk about the recommendations that this working group just released the end of May. It's early days for this. We're trying to think about generative AI and analysis. So that's where we're heading. So again, this is obviously an unnecessary slide. It's highly parochial. I only read MIT News, it turns out. That already is too much. I can't keep up even with that. But the idea of the outrageously exciting opportunities that have already begun to unfold across the natural sciences is just, it's an accelerating drumbeat, and increasingly even in humanities and social sciences and so on. It's not only in some areas, it's now really percolating to many, many parts of the academy, and IAIFI is, I think, a really amazing, exciting exemplar of that. But as I think we all know, once we just pause for a moment, and even if we only read MIT News or go beyond that, there's a series of challenges that really, some of which are really pretty stubborn, that have been identified and thought about and analyzed carefully for years now, and yet we haven't gotten our arms around them really yet. And again, this is a short set of them. We can all brainstorm a longer list, but things that are sort of powered by advances in computing, machine learning, and so on, and that are leading to outcomes that are really, really not things I think we want to celebrate, to put it mildly. I plan to tease your question. Do you want to know what's this Enron thing doing on the screen? Please ask me about the Enron email corpus at the end. But you can see it's ranging a wide gamut. And these are the kinds of things that I first began to learn about in a more intense way when Julie and I began building out CERT. So one of the first things that Julie and I did was launch this case study series. It's entirely free and open access. We don't track you. We don't, try to sell anything or push ads at you. And I encourage you in your spare time to head on over. It's available all the time. And we publish 2 issues per year. Right now the 7th issue came out in February. I literally just this morning got a revised draft for what will then go into the issue 8. So it's coming out pretty soon. And we publish a handful of new original case studies roughly every 6 months. Not quite 30, 25, 26 up already. And as you can see there, it's a peer-reviewed series, and the contributions come from a wide range of types of scholars within the academy, beyond the academy, and they're coming from many subfields within computer science, but also legal scholars, several now by physicists, historians, philosophers, political scientists, media studies, anthropology, and so on. The topics range broadly, as I'll show you in a moment. Each submission is reviewed by multiple senior scholars, and the reviewership is done in equal proportions between experts in computer and/or data sciences and experts in humanities, arts, social sciences. Every single submission has to be kind of legible to a wider range of readers, and partly because we want them to be useful, among other settings, in undergraduate teaching. Kind of no prerequisites, introductory courses, and that could be a course in Introduction to Machine Learning, where many now are used at MIT. It could be a course in History of US Modern Regulatory State, what's the deal with blockchain, right? They're really used broadly, and that's the goal. Half our readership now comes from readers who are accessing the site outside the United States, which I think is also pretty great. And here's a quick sample. I won't go through all these, but you can see just from skimming the titles, about 1/3 of the cases we've published so far, and more, as I say, more on the way. A lot of these cases are really focusing on the intersections or interactions between very exciting advanced techniques in computing, like machine learning and associated AI techniques, and people. Individual people, communities, groups, institutions, legal structures, the people side can scale across a huge range, but that's where a lot of the work has been focused. I should also say these are all quite short. We keep them brief on purpose. Our undergraduate volunteers tell us it takes about 15 minutes to read one of these, and then with a kind of long set of curated references and things to explore further. So it's still August. If you're right, this could get you pretty far. We also have things like this. One of my favorites, I shouldn't play favorites, but one case I come back to often is by Harini Suresh and John Guttag. Harini at the time was a PhD student here in computer science working with John. John's a very accomplished computer scientist. Harini finished a PhD, finished a postdoc, she's about to start on the faculty ground. And so their case was to step back a bit from individual applications of the machine learning pipelines and identify a whole series of points along a typical machine learning life cycle in which all kinds of forms of what we might call bias can arise, because we often hear the phrase algorithmic bias as if it's a singular topic. And instead, what I find very helpful that Harini and John have done, we break that down. There's different types of concerns that arise, and therefore different types of effects, and also maybe different types of potential mitigations. So that's in the series, in the case study series as well. And it's important because many of these algorithms, especially the so-called predictive algorithms, are already deployed in the real world. Not only, so my concern is not only am I going to misunderstand the H to BB bar cross-section, which would make me very sad if I misunderstood that, but it's also being used in facial recognition technologies in a completely unregulated way and leading to all kinds of really quite horrifying false arrests and everything in between, okay? So that's part of what, again, I got my eyes open to when working with the CERT team. Another thing that I think maybe brings us closer to a lot of what we all in this room are also very engaged with and concerned about, something that again became front of mind for me while working with CERT, is the question of impacts, sustainability or environmental impacts. So we've heard a lot about, say, the number of trained parameters in the various generations of GPT. So this is the number of ML parameters, and we saw we've now passed we're now at roughly 2 trillion trained parameters in GPT-4, lead by 10 over the 3-year gap there. What we focus on, I think, less often is what it's taken to get there. Here's the electricity usage just for the training phase, let alone usage now by end users in the cloud and all that. But just to train each of these generations, yeah, please.
Is that number accurate, the 1760?
According to a Google search, I'm not an expert.
Because they are really trying to hide that number.
I know, I take your point. Let's just say order of magnitude trillion, that's what gets us to what we need here. The point is, there's a jump, I think people agree, there's a jump by about a factor of 10 here. A jump by about a factor of 50 in the electricity consumption to train that model, train that generation. So the consumption was scaling more steeply than the number of parameters, whatever the number is, right?
I'm completely in agreement.
Yeah, no, it's a fair point, so I take your point.
Point of normalization for gigawatt hours, I don't know how to.
Yeah, I'm good. You're good. So a typical commercial nuclear reactor works at the hundreds of megawatts or gigawatt scale. Another thing about this that again might help with this room is that now the training GPT-4, just training it, was 20% of the electricity consumption of running all of CERN for a year. Maybe that's a good local measure that makes a bit more sense. I'm not suggesting we turn off CERN or that we don't make more GPTs, but that's the scale that now we're up to.
In the experiments, not just the buildings.
Running all of CERN, not just operating the LHC, but all the other good stuff that happens in CERN as well. Keeping the lights on for a year, let alone smashing protons, right? So now we're at 20%. And so again, that is not on its own sort of good, bad, or otherwise, but that's the kind of consideration, a scaling that I think is worth keeping front of mind. And again, to help me think about that, I turn once again to one of these case studies by a really brilliant young colleague, Stephen Gonzalez Monserrate, who finished his PhD here in anthropology of science. And so Stephen did sort of years and years of in-depth field research, ethnographic field research, at a series of so-called data servers, data farms, for cloud computing, not necessarily for GPT, but this sort of larger phenomenon of ubiquitous computing. And he was talking with computer scientists, but also technicians on the ground, people who live near the centers and so on. And so beyond even just electricity consumption, which is easier to plot, there's an enormous concern about water consumption for cooling these sites, noise pollution, thing I had not recognized at all, but I learned really from Stephen's work. A lot of these server farms are considered separate from industrial manufacturing. So they have a kind of loophole cutout from noise pollution regulations that otherwise apply to like factories that make stuff. Even though some of these sites are putting out enormous amounts of noise, you just count the decibel levels and then reputable reported instances of making neighbors sick, e-waste and so on. So again, this doesn't mean a GPT love it or hate it. It means a set of dimensions that I think we should get better at considering. And again, a little more to read. Very recently, my colleague Jaco de Swart, who's an historian of science, teamed up with Ansi Thresher, who's a philosopher, and Carlos Arguelles, who's a neutrino experimentalist, with this very interesting kind of comment piece in Nature Reviews, and also as Ian Paul mentioned, similar work. So again, it's not that no one's thought of this, but I think we can get better at making this a reflex. Let's think about this at least as often as we think about other elements of these toolkits. Another one that's come up a lot, but again, I began to appreciate through the CERT work, and I think it's another point of clear contact with the AI and the natural sciences. It is a question of interpretability. Again, you're going to see a pattern. I'll point you to a certain case study. That's all I read. And here's an interesting one that came out again quite recently by colleagues who were at the time based at Lincoln Lab. They were focusing not on GPT models, but on something called signal temporal logic, which is one of a set of so-called formal methods for trying to get humans to be able to interpret the way that a trained ML system is doing what it's doing. And so I won't bother reading through this. This is just from their case study. The idea is they actually ran a test with human users. I'll describe very briefly. They were training an ML system to do a game called Capture the Flag, and to start, the red opponent won't even move. So could the ML code up instructions that will get the blue dot to capture the flag, even when the red dot isn't even moving? And the idea is to then recode what the ML is doing in 3 different forms of human readable or human interpretable representations. And have humans say in advance, will this work or not? Is it going to accomplish the goal or not? So then they recruited 62 test subjects, 13 of whom had quite advanced training with formal methods, including STL, and the others of whom were, by their own admission, new to these techniques. And the idea was many of these algorithmic systems are going to have end users who are not PhDs in a relevant field. So they wanted a mix of people with familiarity and without. So the first thing is that people were really bad at this. This is the sort of gold standard interpretability for ML. This is one of several that you'll see lots and lots and lots of papers about claiming this will now do interpretability. And both well-trained users and novices were actually pretty much the same, and they're pretty bad at it. You're pretty bad. So there's a weak correlation with having a PhD in the field versus basically invited because you saw a flyer on the metrical on the T. And nowhere were we getting anything like 98%, goodness here to make sense of what is supposed to be the machine telling us when it's doing a human readable form. However, there was a remarkable correlation, which is the people who had training were wrong as often, but much more sure they were right. That seems to be true across academia, right? So here's where there was actually really statistically significance between the 2 types of communities of users, right? And so that again gives me pause. We hear a lot, rightly, about kind of human in the loop. It's a black box. We'll keep people interacting. So well, that's not so straightforward either. So let's keep that in mind as well. So that's a kind of background of some of the things that I really learned more about from working with some amazing colleagues and students across 20 different departments at MIT over several years. It was really quite a ride. I want to turn now to this work by my friend Bruce Bassett, who's also a theoretical cosmologist, and Bruce has gotten very interested in data science and ML in the last several years. And so I worked with him on this case study he published in a series just 6 months. It was in a winter issue. And I think this one, again, like Aesop's Fables, it's a simplified story, but I think it helps to highlight or bring to the surface a bunch of themes that I think are actually much more deep and we want to sit with. So again, in this room, I don't have to linger on this. What Bruce focused on in this exercise was this really still remarkable discovery from roughly 25 years ago. That the universe is not only expanding, it's getting bigger faster, what we would now call the effects of dark energy. And again, as these folks in this room will know, that was first really kind of indicated empirically by these observations of type 1a supernovae and comparing a measure of their distance, basically their apparent magnitude or distant modulus, with how far they're moving away from us, their redshifts, okay? And this is, as again, folks will know, a group led by Saul Perlmutter based at Berkeley, another group led by Adam Rees. They, together with Brian Schmidt, shared the Nobel Prize a few years ago for this really quite remarkable and very important discovery. So Bruce then said, this was done in November this past year. This was GPT-4 era. So he basically, for years, he's been assigning a really, I think, clever problem set to his master's students in cosmology. And he said, let's do the same thing for a combination of GPT plus what was then called ADA. That's been renamed, but this advanced data analytics, again, a kind of plug-in generative AI tool that's meant to interface with ChatGPT. So the first task that he assigns to actual human students is load the publicly available Berkeley group, the Perlmutter group supernova data from 1998, load that up. Well, it turns out by design, ChatGPT and ADA can't on their own search the web. So Bruce actually manually uploaded the raw text data as an Excel file, being cheeky with no labels. He just loaded up, columns of data. And the tool actually had difficulty parsing it, partly because of formats, but then after 4 unprompted attempts, Ada figured out this is data about supernova and figured out what each column was. That already boggles my mind. It makes me excited and scared in equal proportions. And so Ada actually sort of passed that test, dealing with different constraints than Bruce's human students do. Then Bruce asked the tools to compare the inferred data format. Is this column distance modulus or what? with information available at this website, and Ada replied to the ChatGPT interface. Certainly, let's review the data format. Our extracted columns align perfectly. It can't access the web, right? So Bruce said, how did you do this task? And it said what Bruce wanted to hear, not what was actually true. So Bruce knew this and then added a direct prompt. Okay, well, then the robot says, I did not access the file. I relied on the description you provided, which was minimal, so that's also not. The point is, this is an unreliable reporter of the methods used, even in response to direct follow-up prompts or queries, okay? And we've seen this with chatbots, ad nauseum, but even in this really restricted domain. Next, the next part of the assignment is to calculate this very famous distance redshift relationship in a simplified time model that many of us knew and loved until 1998, called the Einstein de Sitter model. In modern parlance, that's a spatially flat, Friedman, Lemaitre, Robertson, Walker line element with matter domination, no cosmological constant, one form of matter. And so remarkably, ADA found the appropriate equations, found things like the Friedman equation, or called up from its training, the Friedman equation, but then, like all of us do, set the speed of light to 1, and so therefore all the numerics were off. So Bruce gave a follow-up prompt, restore your units, try it again, and ADA complied. This part I love. Next, ADA tried to evaluate one of the integrals of this one. This part is the only integral I can still do without looking it up. X to the D, anything else, I'm going to mathematics myself. And ADA couldn't do that. Again, we've seen lots of examples of this, even just simple arithmetic. So it's an example, just like what Matt Schwartz was saying, don't ask these tools to do those things, go to a kind of sandbox or plugin. You can see that it's going to be really, really far off the answer that it came up with compared to the correct expression. So Bruce prompted saying, can you do the same thing using SymPy, which Ada can access? And I got the correct result kind of instant, immediately. So with a little human in the loop, there's a way to be sort of self-correcting here. Next, Bruce says, plot a corrected analytic curve, the one done through SymPy, alongside the supernova data. And out came this, in a blink of an eye. And again, this is remarkable. Bruce didn't say label your axes, put a legend on. Ada was already producing scientifically appropriate, clear, easy to read plots with very minimal human interaction or prompting. I think that's really pretty amazing. And then Bruce says, okay, now I guess he would do with his master students. Now let's make it a slightly more complicated situation. Let's go to what we now call a spatially flat lambda CDM model with 2 free parameters. And he enters it like this. He doesn't explain what all these things mean. He just uses the jargon of our field and infer best fit values for the present rate of the expansion, the so-called Hubble parameter, and the amount, the fraction of the energy density in our universe that will be contained in a cosmological constant. So with no additional prompting, Ada wrote the MCNC code itself, and then had to get over its own imposed roadblocks. These things have 2-minute execution time limits. And so, oh, that's fine. So we just rewrote its code to be increasingly more efficient. Right, that's amazing. This is why the robots will rise up. And in less than 5 minutes to produce these plots, which are unbelievably accurate given the data at hand. They're unbelievably helpful. And so as the real world groups had concluded, our universe seems to be much better fit by being dominated by a cosmological constant, and it can even give confidence levels for sort of a lower bound on the value of omega lambda. Then Bruce says, we'll plot the model with best fit parameters in the MCMC alongside the data, and you get the really quite beautiful thing. And that, roughly speaking, is what got our 3 friends the Nobel Prize, roughly speaking. So I shared this with Saul Perlmutter. I said, the robot did this in 30 minutes. Pretty amazing. And again, even master students working very hard with guided tours can get there, over like a week or 2, right? It's not like it's impossibly hard to do, once we know where we're going to get to. But Ada, with minimal prompting, did this basically in 30 minutes. However, it also tries to tell us what great work it had done. And it shows that the non-accelerating, non-cosmological constant fits the data better. Oops. I mean, so the master students come away hopefully saying, oh, the upshot was a scientifically relevant result drawn on a series of data, and the robot wasn't quite there yet. Okay, so we might want to separate kind of understanding from manipulation. Again, if we're going to keep humans in a loop, then maybe this is not the biggest failure mode, but it was, I thought, quite striking. Last part, Bruce then says, take a random subset of the existing data that was given to you. They have the whole entire Perlmutter group data set uploaded. Bruce says, take a random subset and compare those with various model predictions, and this is what Ada produces. This is where I start getting very nervous, right? So here's the actual curves and all the work to pick here, and it tells Bruce this is a subset of these data. The black is meant to be drawn from the red. That is a hallucination of cosmic proportions, right? That's really bad. Now, of course, this is trivial as thought because any of us can see, oh, that clearly is just, to be polite, a hiccup. It's a catastrophic failure. What happens when the hallucinated data are more difficult for us just to spot, right? So to wrap up this middle part, these tools were, even simplified versions, much, much simpler and kind of off the shelf compared to these very sophisticated things that I've learned about from your talks over the week. Even these kind of commercially available tools could do really amazing things with minimal human prompting and do them actually really quite well and quite fast. Along the way, it makes the kinds of elementary mathematical errors that we already know to be we were primed to watch for, and we can work around. It fails to connect kind of resulting interpretations, but maybe that's what humans do especially well. Maybe that's okay. But the ones that really get me nervous are these, where it's actually just misrepresenting the steps it used in response to direct probes, and then doing this kind of a dream state for cosmological data without throwing up a warning saying actually maybe someone should double check that, or I have 38.4% confidence. None of that. It just says sure. Here's my random sample from the data you gave me, right? So these are things. That's what I mean by like Aesop's fables. People are doing much more sophisticated things than this, but I think I don't think these concerns have been erased yet or So let me then very quick, last few minutes here, talk about what the National Academy's working group's first set of kind of preliminary recommendations were. These are just published in PNAS in late May. And so the Academy put together a panel of 24 people, many Academy members from the natural sciences, engineering, and medicine, including several Nobel laureates like Saul Perlmutter, which is pretty great. And then a bunch of experts as well from a bunch of, let's say, adjacent fields like legal studies, political science, philosophy, history, sociology, and so on. The participants also included people with a range of types of experience, lots of university faculty, of course, right? But also former federal regulators, former directors of national labs, or deputy directors, leaders in both, I should say, nonprofit philanthropic foundations, as well as in industries that are working in this space. It was, I thought, a pretty interesting range of sets of eyes on these topics. And then, as I say, our challenge was not to solve sort of AI in society once and for all, but look a little bit more narrowly on generative AI and the natural science. And to start the year's worth of working meetings off, they commissioned a series of these kind of briefing papers, which are now available in the NAS magazine. So Mark and I wrote this kind of historical one. Let's look back to previous instances of once new tools and techniques, and how have sort of scientists and broader society come to make sense of them and figure out ways to use them mostly for good. And then essays by political scientists, anthropologists, philosophers, sociologists, and indeed from leading scholars in AI and ML as well. Those are all. So in this very brief kind of opening set of recommendations, I'm just going to walk briefly through the 5 points that were highlighted. First of is this, we divided up the recommendations for the scientific users who might not always be the same as people who are creating and refining the model. And what we want each group to be cognizant of might not always be the same. But the first was to clearly disclose the use of these tools in research, attribute and distinguish between what's coming from different sources, and then make sure that it's actually the humans whose names on the byline who really are responsible for what they're publishing, including things like proper citation and all the other kind of scientific integrity things that we hold each other to anyway. Those who are making and refining the models should either provide accessible details about the form of training, understanding that the actual training data and so on might be either proprietary or not helpful to look at. But they should be telling the end users something useful about the means by which these models were trained, and also allow archive older models and get something towards replication studies, maybe using some of the techniques like we just heard on the previous talk. That's part one. Part two, scientists are accountable for the accuracy, the reliability inferences, and talking about what led them to a certain conclusion, since machines actually aren't probably going to do that for us very well, and that's a human judgment kind of activity. And therefore, the model creator should be getting better at disclosing limitations. What's the calibration methods with which one can assert a kind of level of confidence in this or that output. Document the AI generated data so that we don't have this thing like what happened with Bruce's kind of toy model study, where these data are clearly kind of synthetic, and yet were claims to have been taken from a direct observation of a supernova. right? We better get very good at telling you the difference between, let's say, real and simulated data and marking them as such, worrying about things like provenance, and so on. A focus is very broadly on ethics and equity. These tools are amazing and powerful, and they're not only going to stay in the laboratories. And that's the lesson over and over again of things like facial recognition technologies or natural language processing, which are out there in the world being used in the US in almost entirely unregulated ways, sometimes for very great things, sometimes for really pretty bad things. The tools we make here don't only stay here, right? So let's keep that in mind as we refine these incredibly impressive and powerful tools as well. Let's do it while trying to promote equitable access. We don't want only the rich getting access to really rich tools, expensive tools. Let's be respectful of the things we already should have been thinking about. And then let's not start abrogating topics of clear human judgment to the robots. These should not be used for peer review. These should not be used to determine who gets tenure. Note of that, right? They should not be used for who's going to get a grant. One of our biggest concerns in the working group wasn't that the robots will rise up and kill us all. It wasn't that we'll all be out of work. Is that this is going to flood an already frail system with reams of mediocrity. But the bar to get something that looks like a minimum publishable unit has been lowered by people who might not have domain area expertise or might not have been super careful what was synthetic versus empirical data. That we have a kind of rickety system of things like peer review and human interpretation that is in danger of being overwhelmed by a tsunami of not great stuff, even though the tip of that distribution is outstandingly inspired. So let's keep our eyes open on that. And finally, this is clearly a moving target, right? So the last recommendation for this group was that the national academies should appoint a new standing committee for which there's precedent in the biomedical sciences and other areas. It should be a standing committee because this isn't, we're not done. So let's make what's called a strategic council on basically best practices. And that group should operate at a reasonable cadence and keep the larger community aware of things that are working really great and things that now still need some more careful attention. So let me wrap up. These techniques are fantastic. I don't have to tell this group that. And my head's, spinning already from the things I've just heard about in just a week alone. But like any new tool, they carry risks and unintended consequences. Even the most, kind-hearted, equity-focused human researchers are making things that they don't get to control the uses of once it leaves their laboratory, even if they don't have malicious intent at all on their own. And we have lots and lots of historical examples of other things like that in the US and in many other parts of the world, we've had to learn over time to try to deal with. Let's not forget those insights now. And so in particular, I think about these kinds of bullet points, and I'm sure the group here can fill out a longer list. A disconnect between what we might call results and interpretations, misrepresentation of what was actually done, and that's beyond kind of technical discussions of explainability or interpretability. This one with the sort of hallucinated data, again, was especially alarming to me. How do we get to something like uncertainties or something systematic about what otherwise looks to be black box, often stochastic processes? And then let's make sure we don't flood an already important but kind of under-strained social system with a lot of not great stuff. Thank you.
Fascinating talk. Do you have questions?
I'm glad that you were actually taking this leadership. But we have to also understand it's a global problem, right? It's not just the United States.
Of course, I agree. Yeah.
And we always are scared that there are rivals, probably almost at the same level.
Yes.
Or maybe even better. The challenges. Is the committee thinking about those things?
Yes, and not with one voice or one mind, but certainly in these discussions. Let me start by first saying again, I went by quickly. One thing I'm in a very small way very proud of is that this case study series, one more plug for the case study series, is that our readership now is 50% people from within the US, 50% from outside the US. The US is not 50% of the world population, but still that's a reach. And it's basically we have at least some readership now on every continent but Antarctica. So it's not only Western Europe. The topics of the case studies, I work very hard in commissioning some as well as accepting submissions on their own. I encourage you all to get in touch if you have something you'd like to write up for the series. But also actively commissioning examples that are also drawn by and focus on parts of the world outside of the US or let's say Western Europe. by subject area experts who themselves are based elsewhere. So I should be clear, authorship in the series is open to anyone. It's not only MIT authors. So that's in a very small way saying exactly what you say. This is a global challenge and it's inflected differently. It's not that the challenge of facial recognition technology is the same here as in China. It's a really fascinating piece in the series. Public attitudes toward the government use of facial recognition technology in China, which is difficult to assess, but is a team of anthropologists and legal scholars and Chinese historians using certain kinds of information surveys. Say that what floats to the top of the concerns, at least as represented there, is different from what we tend to hear about in the US, and yet I'd say also quite significant and important. So that's a quick example. Another thing I'll make a plug for history. Everyone should take more history class now. I hate to say that, it's true. When you talk about sort of nation by nation challenges, we've seen that over and over, right? That phenomenon and its role in driving sometimes fantastically exciting science technology, but not in a vacuum. And also, and sometimes not so great outcomes. The thing about most recently, say the Cold War, but it's not like that, like internation rivalries were invented, in 1948 either. So that's an example where I find it helpful to turn back the clock, look at other parts of the world and other periods of time where we can see, do the usual kind of compare and contrast. Some things sound like kind of pre-echoes of what we are immersed in today. Some things look different. It's also an empirical experiment that humanity's run over and over again, right, for a long time. So you don't only have to imagine what might happen if, it's like, well, what did happen in a wide range of cases, none of which is identical to today, but that might help bring to the surface things we should be especially attuned to. So we need more historians, and we certainly need to be listening to and thinking about many parts of the world.
Other questions?
So what can the physics and research community do about the incentive landscape
Yeah.
that pushes or rewards people to produce this work, which, as you say, is mediocre and potentially ill-founded or spotty?
Right, something which is amazing. This is not a blanket statement. So, but there's a distribution to it, right? Jesse and I don't know if you remember, Jesse, we were talking informally about some while ago. That sort of as a technical challenge, tagging the provenance of certain data is somehow not insurmountable. But in things like ChatGPT or these kind of commercially produced, very, very large, extremely large language models, what's the incentive either in terms of profit and loss or regulation or anything? Is there any incentive landscape here? And as I'm sure it's different as of today. It's different in the US than in the European Union. It's different in other parts of the world. It's a moving target, sometimes very slowly moving. But I think right now, there's something that again, when I wear my historian's cap, I find absolutely astounding that things like, let's say, all the back end behind social media has gone essentially unregulated in the US for as long as it has, when that was very, very different for once new communication technologies that were heralded in their introduction as being as disruptive and important and maybe dangerous or more so. And that means like the telegraph and radio and early TV. Like we have these examples. We have books and books and books by very smart scholars who have looked at each of those prior instances, none of which is not the identity make. It's not exactly what we face today, but none of those in the US context, or at least in the European context, that I know a little better, compared to other parts of the world, none of those were like, we'll just reintroduce it to the world and see what happens, right? So part of what concerns me is that we have this kind of extreme version of a laissez-faire for decades for some of these techniques, which was not true for any of these other broadly comparable technologies, which are powerful, can do amazing human good, right? Can do great, great good things, but there was a recognition earlier on that there are useful limits, not yes, no, shut it down, right? But useful ways for proper and less proper uses with a bite, right? With a regulatory kind of control as well. So this is my way of saying to you that I'm still frustrated that we are in the US and the EU AI law it's complicated, has lots of things. People have rightly criticized some parts of that rather ambitious set of legislation. We're not there, and I don't see much effort in this country to be pushing there. And that's why I think the National Academies quickly changed its marching orders to the working group. At first it was like AI society, like, come on. You know, in 1 year, so instead, let's have a generative AI in that. Like, let's scope it down a little bit more. Because the National Academies is a reasonable layer in, at least for US-based things, to have something to say with some backing of it, right? So reduce the scope, not to zero, reduce the scope, and then get a wide range of folks in there to help think it through. And so if we can make that a new pattern, maybe that's what takes it perfectly. If it makes sense.
Thanks, David. And let me make a plug for your issues article. It's really great about kind of thinking about AI and other related technologies in the past. And certainly gave me a lot to think about. The National Academy study is a consensus view, yes, of your 24. Can you talk about, for the particular historical perspective, were any of those 5 recommendations that you showed, or there's any ones that there really is like a historical insight that drove one of those recommendations or drove the way that you were thinking about it, or a direct line from your article that you wrote, then kind of to translate into a recommendation?
Thank you, Justin. You know, honestly, that's a great question, and I'm gonna have to get probably 2 more cups of coffee and go back to think about it. So I'd love to chat about it with anyone. Off the top of my head, it's hard to come up with a very concrete bridge. Partly because in a very useful way, you know, as happens, the essays were commissioned far in advance of the first meeting. Tons of feedback, very smart, constructive feedback from readers. 2 rounds of that. We were about, you know, so it actually became part of a discussion as opposed to this prompts that, which maybe was the point anyway. I think that's true of each of the articles that were published in that special issue of issues. So they were also useful in moving targets because it was really a conversation that unfolded in stages over the better part of the year. So I certainly wanted to say that because Mark and I wrote this down on page 3, recommendation 4 is there. Certainly nothing like that. And instead it was a lot of kind of useful feedback back and forth. But I'll try to think more concretely about it. Thank you.
Hello, thanks very much for the talk. I'm curious to know if you have any thoughts about how these policies can be enforced on a short time scale by people who are in the process of practicing, doing the research. So really, I mean, speaking as a grad student, I mean, from the grad student perspective, but really anyone who's actually working on it, because I think it's well set up for things like bringing some type of legal charge against people for infringement on intellectual property. It's well set up for the review process, telling people that they should address some of the concerns with the generative AI. But in practice, before we even get to that stage, what can be done on a short time scale?
That's a great question. Maybe this brings back, I can try to tie it back to Jesse's point as well. Thank you for that question. So one thing that was often voiced in the discussions along the way, not the majority of things that would often come up, is that somehow any kind of regulation of the scientific enterprise is going to kill innovation and be horrible and bad. I was like, science in many ways is the most heavily regulated set of human activities in North America. And it hasn't killed science. And we'll all complain about NSF review boards, and especially those of us that deal with it, IRB, human subjects experimental, review. It's not perfect. It's not optimized to the current situation. But you can't. There are limits on what one can do in a chemistry lab now in a university with federal funding that don't apply, in the same way elsewhere. I mean, this is one example. And so me, not only me, and other of the kind of social science colleagues we brought in, kept saying, what do you mean you can't have any regulation in modern science? It's incredibly heavily regulated with the EHS and IRB and a longer list. So I think there's something to that. And again, I want to say regulation doesn't just mean yes, no, shut it down, you're bad, you're good. Right? Are there productive routines that are subject to appropriate oversight that shouldn't be mechanical, shouldn't be done by robots? It is subject to hopefully human judgment with a range of humans, being able to pool their expertise and their ideas. So in something like training young scientists, we spent, as you know, as most people who know, we spent an enormous amount of time on what we might call kind of oversight and calibration of that, right? So everyone's passing through not just coursework, but general exams and have committees, and the decision can't go into, right? We have structures for tracking the quality and the methods used in producing young researchers and the associated research. We're best instrumented, at least in the modern university framework, I'd say, for this. And so then the question is, do we get more and more folks who have some experience articulating what might be concerns or best practices or things to avoid or things to look out for? And so we haven't done the best job yet in training both the younger scientists who are coming up and their advisors and committees and colleagues to recognize things to talk about now, whereas again, our friends in chemistry or bioengineering, this is not strange to them, right? In some aspects of that kind of infrastructure machinery. So I'd actually try to be a little more hopeful and say we're actually best instrumented in modern universities. We've grown about it a lot, and it's certainly not perfect, but we're not starting from scratch, whereas we tend to be starting kind of from scratch in other areas that have me concerned. So to turn it around and say, let's be a little more hopeful that if we put our heads together in the settings we know best, and frankly, control, or at least have a modicum of control, is that a place we could start? And then the hope is, we always tell ourselves this, that these incredibly bright, well-trained, careful young people will go out into the world in all kinds of directions. They'll start training their own students, they'll go into industry, they'll go into public policy, they'll go into foundations. So the hope is you get a kind of percolation over 1 to 2 generations. It hasn't happened yet, but that won't happen if we're not doing it where we're kind of best equipped already to try. And that's with things like CERC and for many efforts at many universities around the world. I think that's one goal to build toward that from the overt training phase.
Yeah, thanks. This is really interesting and important work. I actually think this might be one of the most important physics results. And let me explain why. Because I think, our credibility is a very important, right?
Yeah.
And if we let junk through, you'll never know what's the good stuff or not.
Right.
But also, I think, we are not going to survive as a science community if we don't have a stable and productive society that's educated and understands why this stuff is important. And I think if that stuff doesn't happen, then we're just not going to be able to do physics.
Right, so we're about to break for lunch, so I'll try to end on a happier note. The gravitational well is quite deep now to pour all of that. Because I agree with you, it's too early to go start drinking. So
It's never too early.
No, okay, that's a separate discussion. No, I hear you, but I do think, again, if we can stretch our muscles, and this comes back into training as well, if it becomes more routine to pause and think about what's the milliwatt hours, let alone gigawatt hours, is going to take to do this routine. And people over this week have already mentioned that kind of thing. And that doesn't mean stop doing all kinds of fancy computing. Of course, it doesn't mean that. But can we think ourselves in a multidimensional space, right? And one axis of which is thinking carefully about, let's say in this one case, environmental or sustainability concerns. That's not pitted 1-to-1 against other things, but can we think in a higher dimensional space a little bit, in moderate more dimensions, and can we begin to factor that into our own decisions? It shouldn't. I don't think it's going to work if it's only individual choice. That comes back to regulatory and or broader systemic things. But there's one thing that at least could help, right? If this becomes part of a habit, because then we'll hopefully get better at articulating why we should or should not build the FCC or next version, JWST version 2 or whatever it's going to be, right? Now that I was talking with a colleague earlier, now that we're at the level of appropriations, where the next big thing is competing not with neighboring scientists, but with aircraft carrier, right? The budgetary and environmental impact, the footprints are no longer kind of benchtop laboratory-based scale. They haven't for a long time. And so if we want the next Planck satellite, the next LHC, or whatever, we should be aware of what we're asking for and why, and that's going to live in a wider space, a multidimensional space. And if we get better practice in articulating why that's nonetheless going to be helpful for these other things we also all care about, maybe that's something on a happier point to sort of aim to, as opposed to only feeling the glue. Yeah, thank you.
We're out of time. Let's thank David.